Our eyes rely on a rigid rule of physics. Light travels in a straight line. If an object blocks it, we are completely blind. In high-stakes environments, that biological limitation is deadly. Stepping up to look over a deep trench or surfacing a submarine to scan the horizon exposes a person to immediate hostile fire. The solution was a mechanical workaround. This angled viewing box allowed soldiers to continuously monitor the battlefield while their bodies remained safely hidden. Overcoming our natural blind spots meant engineering a tool that could physically intercept incoming light and force it to change direction. To understand exactly how that light manipulation works, Dr. Chem is building a working prototype in the lab. The raw materials are basic. All that is required is a long structural housing, like a stiff cardboard box, and 2 highly reflective plane mirrors. While the components are simple, assembling them requires precise optical engineering. A successful prototype will prove that we can construct a physical, geometric highway to safely route light around solid corners. The build starts by creating a long, hollow column. We cut 2 small viewing ports, or apertures, at opposite ends of the structure to control where the light enters and exits. Next, we secure the 2 flat mirrors inside the casing, positioning one directly behind the top aperture and the other behind the bottom. These mirrors must face their respective cutouts and run perfectly parallel to each other. Here is the strictest rule of the build. Each mirror has to be pitched at an exact 45-degree angle relative to the walls of the tube. If the angle is too steep or too shallow, the incoming light will bounce erratically, striking the interior cardboard walls and scattering before it ever reaches the bottom port. Structural precision guarantees optical success. Geometry dictates what we can and cannot see. This diagram illustrates the law of reflection at work inside our prototype. It maps the physics that allows the device to function. An incident ray of light enters horizontally through the top window and strikes the surface of the first mirror. Because the mirror is set at exactly 45 degrees, the light reflects at a 90-degree angle, redirecting straight down the shaft. At the base, that vertical beam hits the second mirror, turning another 90 degrees to exit the lower port. Because the light is redirected twice by parallel surfaces, the orientation of the incoming image is preserved. The picture arrives right side up, without any spatial distortion. By mathematically mapping the law of reflection, engineers can bend reality, delivering visual data safely to the observer's eye. Dr. Kim's finished lab prototype works exactly as intended. Looking into the lower aperture, an observer can observe a blocked object with perfect clarity. This exact mirror and tube rapidly scaled up, becoming a critical instrument for submerged naval vessels. But applying this to a warship required massive mechanical complexity. The periscope evolved into a heavy column of brass, prisms, and thick lenses that took up significant space, requiring multiple crew members to manually operate. Navigating at pressurized depths requires a sealed, continuous structure. A traditional periscope required engineers to cut a large physical hole directly through the pressure hull, so the optical tube could slide up and down. While physical optical tubes provided a tactical advantage, their mechanical requirements created a structural vulnerability. To solve the hull penetration problem, the U.S. Navy equipped its Virginia-class submarines with the modern photonics mast. The photonics mast completely eliminates the need for hollow mirror tubes. Instead, it places an array of high-resolution digital and infrared cameras atop telescoping external arms. This side-by-side diagram highlights the structural advantage. Sending digital signals through small wires, rather than bouncing light down a massive physical tunnel, allowed naval architects to seal the hull and move the control room to a safer, lower deck. Whether it's angled glass in a trench or digital sensors rising above the surface, the core objective remains the same. By understanding the rules of physics, human engineering continuously bends light and data to our will, making the invisible world visible.